Hi, I'm Dr. Omer Munir, and today I will explain how to solve a plane truss problem. Let me first explain what is a plane truss. A plane truss is a structure composed of bar elements that all lie in a common plane and are connected by frictionless pins. The plane truss also must have loads acting in the common plane, and all loads must be applied at the nodes or joints. The common example of a plane truss is a bridge truss, as you can see in the uh, figure at the right top. And another example of plane truss is roof truss. So these are the two examples of plane truss. So our example of plane truss has been taken from a book which is a first course in the Finite Element Method by Daryl L. Logan, 6th edition. The example is 3.5. In this example, for the plane truss composed of the three elements shown in the figure subjected to a downward force of 10,000 pound applied at node 1. You can see that three elements are connected at node 1 and a force of 10,000 pounds is applied at node 1. So let the E Young's modulus is equal to 30 into 10 raised to power 6 psi, and area of cross section for all the element is 2-inch square. So we need to find the displacement of nodes at displacement of node 1, and we need to find its horizontal displacement u1 and v1. Then we will find out the stresses in each element. To our ANSYS program, let's drag static structural in the project schematic. Then we will edit the engineering data. We have the value of Young's modulus. Let's first change the units to US customary, and we have the value of Young's modulus is equal to 3.0 10 raised to power 7. This is our value of Young's modulus. Then close the engineering data, open up the geometry, click the geometry tab. It will open up the space claim in which we will create the geometry. I am using ANSYS 17.2, and in this version the geometry is created in space claim. So I will show you how to create the geometry in space claim. It will take a few minutes to start up. Let's select the plane, XY plane. Look at the plane, and then we'll draw construction lines. But before that, we should change the units to go to File, Units, and then Imperial Units. Okay. Then I will draw a construction line starting from the origin, and its length is equal to 120 inches. And then press escape. Then draw another line starting from the origin, vertical line. Its length is also 120 inches. Press escape. Then I will draw another line starting from origin, and having length of 169.706. Okay, now press escape again. Press the home button to see the 3D view. Then I will select this point and draw a plane here. First, it is not correctly generated. I will delete it and look at the plane, and at this plane I will select it again, select this point and generate a plane here. And now I will look at this plane. So I'm looking at this plane. Now I will draw a circle starting at the origin, and its diameter will be equal to the, as we are given the area of cross section is 2, so we multiply 2 with 4 and then divide it with 3.14 and then take the under root. So we found area diameter from the area which was given. So diameter of this circle will be 1.596. So 1.596, this is the area of this circle. Then I will press escape, press home button, and then press select. I will select this circle. Press the pull button and select this plane and then press Z. Then I will select this surface and drag this arrow and then enter the value equal to 120 inches. So it will extrude the circle up to 120 inches, because in the statement the length of each element was given as 10 feet. I have converted 10 feet into inches, which is 120 inches. Similarly, I will draw the other two members of this geometry. Press the home button and then I will press select button, select this edge and create a plane here. Then I will select this plane and then look at the plane. From this button I will select the plane and then I will look at the plane. Then draw a circle here on the origin its diameter is 1.596. Then press again the home button and then press pull button and then press Z button. Select this area which you want to extrude and enter a value of 120 inches. So this is the second member of this truss. Then we will create the third member. Press select button, then select this edge and create a plane here. Then press home button and press plane view. Now create a circle on the origin which is 1.596. So press again the home button and press escape button, select button and select this point, press Z, press the pull button first. Hide these planes, uncheck, uncheck, uncheck and uncheck. Then select this surface, press Z and now extrude this surface by selecting the pull button, pull and then click and then drag it and enter a value of 169.706. So we have created the three members and our geometry is now complete. This is our geometry. Now we will minimize it and go to the second step, in which I will double click the model button. It will start mechanical solver. It will take few seconds to open up. Now we can see that our geometry has been imported, and then I will click on the mesh, right click. First I will go to sizing, and the relevance center I will change the relevance center to fine mesh, and then I will right click the mesh button and click generate mesh. After the mesh has been generated, I will add fixed support on each of these three elements. Well, first I will zoom in the first element, select this surface, then apply, then I will add another fixed support, zoom to fit, then zoom and the second surface selection button, then select the surface, apply, then I will add another fixed support, zoom to fit, zoom this surface, and select face selection button, select this face, apply. We will add force, right click static structure button, insert force, and we will apply the force on this edge, which is node 1. Zoom in. We will select the edge, go to edge selection button, select this edge, apply. Then we will define the force by components. Enter for y component minus 10,000. Now we zoom in to see the direction of force. It is in the downward direction. You can see here. So force is in the correct direction. Now we will add deformation. Right click solution, insert, deformation, directional deformation, and orientation is x-axis. Now we will add another deformation, directional deformation, and the orientation of this deformation is y-axis. Then we will add stress, equivalent stress, and then we will solve the problem. It will take few seconds to complete. Now we have the solution. So we have equivalent stress in each of the three members. We will probe the stresses in each member. The stress in the first member is 4017, and the stress in the second member is 1496, and in the third member is 1113 psi. Its unit is psi. Now we'll go to the directional deformation. First, directional deformation at node 1, and the directional deformation along y-axis, that means it is V1. So we will probe it at node 1. So it is 1.5929, and due to the negative sign, its direction is towards negative y-axis. And then we will check out the deformation in x direction of node 1. So node 1, this is node 1, location of node 1, and we will probe the deformation at node 1, and it is 4.02 10 raised to power minus 3. Now we will validate our results with the solution obtained from direct stiffness method. This was our problem, and this is the solution of the above given example by using direct stiffness method. The stiffness matrix for this three member truss, plain truss, is given by this equation, in which C stands for cos theta and S stands for sin theta. With the help of this formula, we obtained the stiffness matrix for element 1, then the stiffness matrix for element 2, and then the stiffness matrix for element 3. Now we will assemble these three matrices to find out the global stiffness matrix. How to get this global stiffness matrix is explained in another video, and I will not discuss it here, but we will compare the answers with our ANSYS solution. So first we will compare the displacements at node 1 with this direct stiffness method solution and with the ANSYS solution. So we know that force matrix is equal to K matrix multiplied by displacement matrix, and after applying the boundary conditions, that means node 2, node 3 and node 4, which were fixed, and putting them equal to 0, we have this equation left to solve, and from this equation we can find out V1, which is displacement in x direction, and U1 is displacement in x direction, and V1 is displacement in y direction. So you can see here that U1 is equal to 0.414, and this is our x displacement, which we have obtained from ANSYS solution, which is almost equal to the solution that we have obtained from direct stiffness method. The second displacement V1, which is along y-axis, is also almost equal to the very close to the solution that we have obtained from ANSYS. Now we will compare the stresses. To find out the stresses, we have this formula for stress calculation, in which C matrix is obtained by using this formula, and D is displacement matrix. So the stress in the first member is equal to 3965 according to direct stiffness method, and from ANSYS we have obtained 4016, which is pretty close. And similarly for member 2, it is also correct, and for member 3 is also correct. So we have compared our results. That means our simulation or ANSYS solution is correct.